Hello everyone, welcome back. In this video, we'll be taking a look at continuity. So, if you guys remember, the our traditional definition for continuity was that it's any function that we can draw without lifting our pen from the paper. So if you lift up, so this is a continuous function because we just drew it without lifting our pen from the paper. But if you have a function that we lift the pen from the paper, such as this function, this is a discontinuous function. So although this definition was okay when we were small, but since we're doing real analysis and calculus, we need a more rigorous definition of what continuity really means. So the more formal definition of a continuous function is the one I've written right here. So let f of x be a function and c d be the domain of the function, and with a being in the domain of the function. We say that f of x is continuous at x equals to a if the limit of f of x as x approaches a is equal to f of a itself. So if we have, so instead of L right here, before we had L, but now we have f of a, it's equal to f of a itself. So the limits must exist and equal to f of a. So let's take a look at an example. So consider the function, okay, let's go for a more traditional function. Okay, consider the function f of x equals to x squared right here, f of x equals to x squared. So if the limit of so let's put some holes in this function. Let's say there's a hole right here. So if this is 2 right here and this is negative 2, so we say the function f of x is continuous at 2 if the limit of f of x as we approach 2, as x approaches 2, is equal to f of a, and f of a right here, since f of x equals to x square, f of a right here should be equal to 4. So if the limit of f of x, if the limit of f of x as x approaches 2 is equal to f of a, which is 4, then we say it is continuous. But if you have, okay, let's consider this point negative 3 right here. You're normally, and this is the point right here, when in this weird function f of negative 3 is defined as 1. So in this weird function, as x approaches negative 3, we have the limit of f of x as x approaches negative 3 as negative 3 as 9. So this is 9 right here. But we know in this weird function that f of negative 3, which is f of a, is 1. So we have that 9 is not equal to 1. Therefore, this function is discontinuous at negative 3. So that's what continuity means in a nutshell. So before we look at some examples, let's take a look at the sequential criterion for continuity. Just as we had one for functional limits, so this is pretty much the same for continuity. So we say that f of x is continuous at a if and only if for all sequences a n which tend to a, f of a n also tend to f of a. And we say that f of x is discontinuous at x equals to a. So this is basically just the reverse of the first statement. If and only if there are sequences, so there are sequences an and bn which tend to a, so there are two different sequences which tend to a, but the limits of f of an and f of bn are different. So then we say they have different the function is discontinuous at that point. So let's take a look at this example. So I'm not sure how to call this. I think it's you pronounce it as the Dirichlet's function. I'm not really sure about that, so don't count me on that. So anyway, that doesn't matter. Let's now show that f of x is discontinuous. Sorry about this. Is discontinuous at x equals to 0. So we're gonna show this So there are two ways to show it. So either we can show it using the traditional definition of continuity, which we did at the start of the video, or we can use the sequence one, which we just did it right before. So I'm going to use the sequence one because it is much easier to do it that way. So consider these two functions. So we need to build two sequences that tend to 0. And this function says that it's equal to 1, which is when it's rational, and is equal to 0, which is irrational when it's irrational. And we'll know from previous videos that rationals and irrationals are really dense, so it's even hard to draw this sequence. So let me give it an attempt. So it's 0 when it's irrationals, and we know there are a lot of irrational numbers, and it's 1 when it's irrational. So we know there are a lot of rationals because of the density of the rationals and the irrationals in the reals. So we can see that it's discontinuous. But now let's go ahead and prove it at one point which is 0. So let's build two sequences an and bn which tend to 0. So we have to build two sequences which an and bn which are rational and irrational. So that'll be a good strategy to show that it's discontinuous at 0. So take an as 1 over n. So we get that an is always in the rationals, and an of course tends to 0, and choose bn as pi over n, and we know that pi is a irrational number, so it'll always be in the irrationals, so it won't be in the rationals. So bn will not be in the rationals, or bn will be in the irrationals. And we know that bn tends to 0. You can also choose bn as a root 2 over n or e over n, but pi over n is a nice way to put it. So we have that f of an. So f of every rational number, for example, an is the sequence 1 over 1, 1 over 2, 1 over 3, and we have that every rational number is equal to 1. So we have that f of an is equal to 1. So we have that limit. So it'll always be equal to 1, 1, 1. So we have the limit of f of an is equal to 1. And we have the f of bn is equal to pi over 1, pi over 2, pi over 3. And we always have an irrational number there. And we have that limit. And so I'm sorry, this is the sequence bn, and we have that f of bn will always be equal to 0, 0, 0. So limit of f of bn will always be equal to 0. So we have two sequences that both tend to 0, but we have that limit of f of an is equal to 1 and limit of f of bn is equal to 1. So they have different limits, therefore they're discontinuous at x equal to 0. And we're done with that example. So let's take a look at continuity in a statement in a nutshell. Basically, this is what continuity all it is. So it says that limit of f of an, limit of a sequence of terms f of an right here, should always be equal to, so if you have the limit, so all these terms are tending to the one certain point L. So if a function is continuous at a particular point, we say that limit of f of an should be equal to the f of the limit. So we have this sequence right here, an, which tends to a, and we know the limit of an is equal to a. So if a function is continuous at the point a, then limit of f of an, which are these terms right here, limit of these terms should be equal to f of this limit of a. So limit of f of an should be equal to f of the limit of these ones right here, limit of an, so which is equal to f of a. So if this is equal, then we say the function is continuous at that point. So remember, in this video we're looking at continuity at points right here, continuity at different points. In the next video we'll be looking at continuity as at the whole graph. We say that it's continuous everywhere. So let's consider this weird, strange function which is called the Thomae's function. So it was made by this great mathematician called Thomé. Right. So he defined his function this way. He said that f of x equals to 1 when x equals to 0, and it's 1 over n when x equals to m over n. And remember, when x equals to m over n, that just basically means whenever x is a rational number, then it can be written as 1 as a fraction. And he said then whenever it gets written as a fraction, then we take it as the 1 over n. So for example, if you have this rational number 8 over 3, then f of 8 over 3, f of 8 over 3 will be equal to 1 over 3, which is 1 over n right here. And it's equal to 0 whenever it's an irrational number. So let's see, let's try to use this statement to show that this function has a weird property of being continuous at every rational point and continuous at every irrational point and discontinuous at every rational point. So let's try to use this statement we learned before and apply it to this function. So remember the intricate way that the rationals and the irrationals fit inside the R. So we proved in a previous video that the rationals and irrationals are really dense. Between any two real numbers, we can always find a rational number and an irrational number, and we proved this in a previous video. So let's so we can always build a sequence of irrational numbers or rational numbers which tend to any point in the real number line. So let's say if C is a rational number, then T of C, f of C will always be greater than 0. Why is that? Because since C is a rational number, and we have that f of C will always be positive. So example, if it's 0, and if x is equal to 0, remember 0 is a rational number, we have that it's equal to f of x is equal to 1. But whenever C, any rational number is always greater than in this function, any rational number, the f of the rational number is always greater than 0. For example, if you have a rational number negative 8 over 9, f of this number will be 1 over 9. And for example, f of 2, which can be written as 2 over 1, will be 1. F of 1 over 3 or 1 over 1, let's say, okay, 10 over 3 is equal to 1 over 3. So we have that in this function, every rational number is always greater than 0. F of C is always greater than 0. But because the irrationals are dense in the real numbers, we can find a sequence yn in the irrational numbers converging to C. Because irrationals are dense in the real numbers, we can find a sequence yn which converges to the rational point C. Right. But we have that all irrational numbers in this function, all irrational numbers are equal to 0. So f of yn will always be equal to 0. So f of y1 will equal to 0. So let me do my scratch work right here so I don't mess up with the proof. So f of y1 is equal to 0. F of y2 is equal to 0. F of y3 is equal to 0, and so on and so forth. So we have that limit of f of yn is always equal to 0 as n tends to infinity. All right, but we have that. Okay, now what next? But we have that f of C, which is f of the limit. So this sequence tends to 0. But remember, from this statement, to prove that a function is continuous, we have to say the limit of f of an is equal to f of the limit of an. So the limit of an, which is the limit of yn right here, is c. So the limit of yn, so the limit of yn is c, and f of that limit and f of c we know is always greater than 0. But we have right here that limit of f of yn is equal to 0. So from this statement, so this is the continuity statement. So this statement does not hold for the rational point, for c in the rational point. So this, from this statement we get that since the limit of f of yn is not equal to 0, but we get that f of the limit of yn, which is c, so f of c is greater than 0, we get that it is discontinuous. Since this statement is not true, it is discontinuous. It is discontinuous at every rational point. Now let's prove that it is continuous at every irrational point. So just like before, let's choose the irrational number root 2. Right, root 2 is an irrational number. So because the rationals are also dense in the real numbers, we can find a sequence of rationals that converges to root 2. So, and that's a pretty easy one to find. Just consider root 2 as 1.4 as a sequence. Consider the sequence 1.4, 1.41, 1.414, 1.4142, 1.4121. So this sequence is converging to root 2. So this sequence of rational numbers, all these terms are rational numbers because they can be expressed as fractions. 1.4 can be expressed as 14 over 10, and this 1.41 can be expressed as 141 over 100. So all these terms in the sequence can be expressed as rational numbers, and we have these rational numbers converging to root 2. So when we now have a sequence, let's call this Rn, that converges to root 2. So using this statement right here, from the left hand side we have that limit, and remember this Rn, so f of Rn, so f of R1 will be 1 over 10, f of R2 will be 1 over 100, f of R3 will be 1 over 1000, and so on and so forth. So the limit of f of Rn, the limit of f of Rn as n tends to infinity, so the limit of this this sequence f of Rn, so f of Rn is this sequence 1 over 10, 1 over 100, 1 over 1000, and we notice that this sequence is becoming smaller and smaller. We have 0.1, 0.01, 0.0001, and we so on and so forth. This sequence f of Rn tends to 0. So from the left hand side of this statement, limit of f of Rn, it's equal to 0, and we also have that f of the limit, and we have f of Rn which tends to 0, and we have Rn right here, Rn which tends to root 2, and this statement says that f of the limit of an and f of the limit of Rn and f of the limit of Rn, so Rn, limit of Rn is equal to root 2, and we, from the right hand side of the statement, we have, so remember we have shown that left hand side of the statement, limit of f of Rn is equal to 0. Now we have to show f of the limit of an, which is f of the limit of Rn. So limit of Rn here is root 2, so f of the limit of Rn, which is equal to f of root 2, and we have that f of root 2 is equal to 0. So we have that f of the limit of Rn is equal to 0. Why do we have f of root 2 as equal to 0? Because remember, this function is defined such that all irrational numbers, all numbers which are not rational, are equal to 0. So we have that f of the limit of Rn, which is f of root 2, is equal to 0. So we have that left hand side and right hand side are both equal to 0. So this statement right here holds, this statement is true. Therefore we have that it is continuous. This function is continuous at root 2, and hence every other rational point. We just chose root 2 as one rational point at root 2, and every other, I mean, irrational point. So sorry about that. So sorry about that. Every irrational point. So hope you guys have enjoyed this video. See you next time.